Hi, what's up? Here we'll be going through second law of thermodynamics. First of all, we'll be going through the list of subtopics. First, we'll start with some basic definitions, that is thermal energy reservoirs. We are having two types of thermal energy reservoirs, that is source and sink. Then we'll be going through statements of second law of thermodynamics. We are having two statements, that is Kelvin-Planck statement and Clausius statement. Then we'll have to go through few concepts like heat engine, refrigerator, heat pump, and efficiency of heat engine. Similarly, for performance of refrigerator and heat pump is given by COP, coefficient of performance. It is similar to efficiency, but it's slightly different, and we'll see how it differs. Then we'll be going through Carnot cycle and Carnot engine, and we'll be going through Carnot's theorem also. Then we'll be going through efficiency of a reversible heat engine and COP of a reversible refrigerator, similarly COP of a reversible heat pump. Finally, one of the most important topic, that is Clausius inequality. From this topic we can expect 3 to 4 marks or 3 to 5 marks, or on average we can take it as 4. Now we will see the brief summary of the topic. First of all, we see what is the need of second law of thermodynamics. We already seen various questions, various process in which when we are applying first law, that particular process is happening and that particular process is feasible also. Then what is the requirement of a second law? Now let me tell you an example. Now consider a car that is climbing a hill, okay, in which what's happening, the chemical energy of the fuel or chemical energy of the car is being converted into potential energy, right? Now imagine the reversible process, that is car is coming down, and according to, if you are considering a hypothetical process, that is potential energy of the car is being converted into chemical energy of the fuel, and we are getting more and more fuel as the car climbs down. You understand that process? That is just reverse of the initial process. When the car climbs down, its potential energy is decreasing, right? And we are assuming that that particular loss of potential energy is being converted to gain in chemical energy. Thus fuel of the car is increasing. By first law of thermodynamics, we can easily prove that that particular hypothetical process is possible. That's nothing but just energy balance. But we know that that particular process is impossible, right? And here comes the role of second law, that gives a direction for any process. By just merely following the first law of thermodynamics does not ensure that that particular process will happen or feasible. I just gave you an example. Consider another example. That means, that is, we are having a coffee, a hot coffee, a cup of hot coffee with me. We know that if you are keeping at a room temperature, it will lose the heat from a cup of tea to atmosphere, right? As a result, the temperature of the coffee will decrease. Anyway, that is according to first law, and we know that that is practical also. We see this every day. Now consider the reverse process, that is the hypothetical process in which the cup of coffee is absorbing heat from atmosphere, and it is getting warmer and warmer or hotter and hotter. The temperature is being increased. Anyway, by first law of thermodynamics, I can prove that particular process is possible. That means just energy balance, gaining heat from outside and surrounding and transferring to system. That's possible. But we know that again that particular process is impossible. There comes the need of second law of thermodynamics. I hope by this time you understand what is the need of second law of thermodynamics, right? Now, as I said, we'll be going through some few definitions like thermal energy reservoirs. We are having two thermal energy reservoirs, that is source and sink. First we will go through source. Source is defined as, it is a thermal reservoir which is capable of supplying heat without undergoing any temperature change. Now consider a bucket which is having hot water. We know that when its heat loses to surrounding, its temperature will decrease, right? but if it has to be considered as a source, its temperature should not decrease. Consider a case of furnace where we are supplying the fuel continuously. As a result, it is able to supply the heat to surrounding continuously, but see, as we are supplying the heat as we are supplying the fuel continuously, its temperature is not reducing. That body we can consider as a source because it's continuously supplying heat, but its temperature is not reducing. Okay, now let's go through the sink. Sink is nothing but again a thermal energy reservoir which is capable of accepting heat without undergoing any temperature change. Take the case of the same bucket of water. If you are supplying heat to water, that bucket of water, we know that its temperature will rise, right? But if it has to be considered as a sink, its temperature should not rise. So how can we model a sink? Consider case of atmosphere. Every day morning in our house we are cooking, right? As a result, lot of heat is being transferred from our system to surrounding, that is atmosphere. But does that make the atmosphere warmer, or is its temperature increasing? No, right? It's having infinite heat holding capacity. So we can consider atmosphere as a sink. Similarly, for practical application like sea or river, where in factories and all we will be dumping the waste heat to these water bodies. Since these water bodies are large enough, there won't be considerable change in temperature even if you are dumping the heat to the water bodies. So I hope you understood the difference between or what is heat source and sink. Once you know this, we are in a good position to go further. Next is Kelvin Planck statement. That is, we are having two statements for second law of thermodynamics. First one is Kelvin Planck statement. Let me tell you the definition of Kelvin Planck statement. It is impossible to develop a device operates in a cycle which produces work continuously while exchanging heat with a single reservoir. That means we are having a heat engine. Okay, in order to work that heat engine, it has to get some heat, right? That means from source will supply enough heat to the heat engine, and this heat engine will be converting a part of heat into work, and by Kelvin Planck statement, it has to dump the remaining heat to another source or another thermal energy reservoir. We call it as sink. That means in order to work a heat engine, minimum it has to interact with two thermal energy reservoir. From one it will gain the heat, and to one it will throw the heat. Then only it can work. If there is only one source or only one thermal energy reservoir from which it is gaining heat and it is producing or it is converting 100% of that energy into work, that is not possible. That's what Kelvin Planck statement says. That particular mission, that is converting 100% given heat into 100% work, is called perpetual motion of kind 2. We already seen what is perpetual motion of kind 1. That was in first law. This one is in second law. Perpetual motion of kind 2 is in second law. I'll explain with an example. Consider that from a source our heat engine is gaining 10 kilojoules of heat. If it is converting the entire 10 kilojoules of heat into work, that means we are getting a result of 10 kilojoule work. We can call that as PMM2, and the efficiency of that particular heat engine will be 100%, right? Heat efficiency is nothing but output by input. Output is 10 kilojoule and input is also 10 kilojoule. So it will be 100% efficient. What Kelvin Planck statement says is that which is impossible, right? So how come a heat engine will be working? It will draw 10 kilojoule from source and it will reject some part of heat into sink, and it will be able to convert only 6 or 4 kilojoules into work. Okay, and we can prove this in practically also. In the class you will see all these things. I am just giving you basic understandings of these ideas. By this time you must be knowing what is a heat engine, right? I already explained you while explaining Kelvin Planck statement, and you know what is efficiency. Efficiency is output by input. Here output is work transfer and input is the given heat supply, right? Okay. Here I have to say one more thing. Heat, we generally call it as disorganized form of heat or lower form of heat, lower form of energy, and work as organized form of energy or higher form of energy transfer. Because we cannot convert 100% of heat into 100% for any usable work, but we can convert, remember, we can convert 100% work into 100% work. That means if you are having 10 kilojoules of work, we can completely convert that into another form of energy, that is work itself. Or if we can convert even 10 kilojoules of work into 10 kilojoules of work or heat. Again I will be telling this, we cannot convert 100% heat into usable form of energy, that is work, but we can convert 100% of work into either it is 100% of work or 100% of heat. Okay, the second law, Kelvin Planck's statement says that only heat cannot be converted completely into work. And next we are going to the Clausius statement. It says that it is impossible to transfer heat from lower temperature to higher temperature without any external input. We know that heat will be automatically transferring from higher temperature to lower temperature body. From our physical experience we know that. And we also know that it is impossible to transfer heat from lower body to even lower temperature body to higher temperature body. Have you ever seen such example? That means you are having cold water and water itself will losing the heat to the high temperature atmosphere, and the temperature of water is going down and it's becoming ice. It's impossible, right? But by refrigerator we can make that cold water to ice. That is called here the external input. That is, by external input we can convert or we can transfer heat from lower temperature to higher temperature, right? Let's see what is refrigerator. We know that refrigerator is a device which maintains lower temperature compared to surroundings. As lower temperature are to be maintained continuously, the refrigerator runs on a cycle. Refrigerator maintains a lower temperature inside the compartment comparing to the surrounding. That's the purpose of refrigerator. You know that, right? And when we learn this, you will be learning the schematic diagram for heat engine, this refrigerator. Similarly, we'll be going through the heat pump also. For that also we'll be going to the schematic diagram. So what I want to say is that whenever you get a problem from this part, first of all you have to draw the schematic diagram. Then you just proceed. Even though you are well versed in this concept, don't go without drawing this schematic diagram, because you may commit mistake. You cannot afford any mistake because this is one of the easiest portion and everybody will be scoring this portion. So you cannot just make any mistake and get a negative mark on this. Okay, similar to efficiency, we are having a term called coefficient of performance, which denotes the performance of the refrigerator, which is defined as ratio of desired effect divided by, or ratio of desired effect to energy input. Here desired effect is nothing but the how much heat is being taken away from the refrigeration compartment, or how much heat is this taken refrigerator is taken from the refrigerator compartment. And here energy input will be the work or energy which we are supplying to the refrigerator. Okay, I'm not going into the details of these things. I'm just giving you an introductory session for this. Similarly, we are having another equipment that is called heat pump. Heat pump is a device which maintains a higher temperature compared to surroundings. In Western countries and all, you know that there the surrounding temperature or will be even go to less than 0 degrees Celsius. But human comfort temperature is around 16 to 20 degrees Celsius. So we need about 16 degrees Celsius inside the room, and outside temperature is minus 5 degrees Celsius. So we have to maintain a higher temperature inside the room compared to surrounding. This is done by using a device called heat pump. By giving a work input or an energy input to this heat pump, which will take away the heat from, which will take the heat from surrounding, which is at lower temperature, and which will be thrown into the heat into the room. Thus the heat content of the room will be increased, and its temperature inside the room will be more compared to surroundings. Here also the performance is denoted by the term called COP, coefficient of performance. This again ratio of desired effect by energy input. Here desired effect is nothing but how much heat is being thrown to the room, and work input or energy input is nothing but the how much work or energy which is we are giving to the heat pump. And there is a relation between COP of heat pump and refrigerator. COP of heat pump minus COP of refrigerant is equal to 1 if both equipments are working between the same temperature levels. And then we are having Carnot cycle. I am not going into the details of Carnot cycle. For here I am going to tell you one of the an important thing, that is for reversible cycles, whether it is heat engine or heat pump or refrigerator, we are having a relation, that is ratio of heat transfer is equal to ratio of temperature. That means suppose Q1 is the heat transfer from the source to heat engine, and Q2 is the heat transfer from heat engine to the sink, and T1 is the temperature of the source and T2 is the temperature of sink. Then we have Q1 by Q2 is equal to T1 by T2. Yes, it's very amazing and wonderful result, which is having a huge impact on the calculation of efficiency, COP of heat engine, refrigerator and heat pump. And you can directly substitute this Q1 by Q2 value is equal to T1 by T2 into our earlier equation, and you will be getting some wonderful result, and you can calculate the efficiency directly. Next, which is again one of the most important part, that is Clausius inequality. It says the cyclic integral of dq by t is less than or equal to 0. It is a tool which is used to find whether a particular cycle is reversible, irreversible or even impossible. If the cyclic integral value of dq by t is less than 0, I can say that particular process is irreversible. If the cyclic integral of dq by t is equal to 0, that particular process is reversible. If this value is greater than 0, we can say that that particular cycle is impossible. Now we can go through various questions or type of questions which is being asked from this topic. The concept questions or one mark question used from this portion is easy and straightforward. If you know the basic concepts like Clausius inequality, efficiency of reversible and irreversible heat engine, COP of reversible and irreversible refrigerator and heat pump, and you know these terms, you should be able to easily score all the conceptual questions from this portion. Here I am having one question which asks an DRDO question, DRDO examination, and it is seems to be very straightforward, but it's a bit tricky. I'll read the question. An inventor claims to have constructed a device that rejects 100 kilojoules of heat to a single heat reservoir while absorbing 100 kilojoules of work during a single cycle of the device. I'll read this question again. An inventor claims to have constructed a device that rejects 100 kilojoules of heat to a single heat reservoir while absorbing 100 kilojoules of work during a single cycle of the device. This device violates. Question is, this device violates. I am having four options. First option is the first law of thermodynamics. The second law of thermodynamics. C, both first law and the second law of thermodynamics. Option D, neither the first law nor the second law of thermodynamics. Here we can straight away say that it is not violating first law of thermodynamics, right? 100 kilojoules of energy is be converted to 100 kilojoules of another form of energy. So I don't think anybody will be having confusion in that. The confusion will be in the next part, whether it violates the second law of thermodynamics. Many people will straight away say that it is violating second law of thermodynamics. But look again, here it is not violating second law of thermodynamics, because here what is happening, the device is converting 100 kilojoules of work into 100 kilojoules of heat. Okay, work can be completely converted to any forms of energy, but it is the heat which cannot be completely converted to work. So it is not either violating second law of or first law of thermodynamics. Interesting question, right? This sort of question you can expect. Generally the questions in gate for conceptual question is straightforward, but still I thought I'll give an example like this. Next, we'll be having problems from the same set of things, that is Clausius inequality, efficiency of heat engine, COP of reversible heat refrigerator and heat pump, efficiency COP of irreversible refrigerator and heat pump, and so on. So I already told you that when you get any problematic question from these topics, first of all you have to draw the schematic diagram, then mark all the given data into that, then proceed, so that the possibility of committing mistake in this short time is very less. Okay, I'll give you an example. Here we are having a cyclic device which is interacting with three thermal reservoirs. Okay, we are having a cyclic device which is interacting with three thermal reservoirs. Out of these three, two are sources and one is sink. They are given the all the heat transfer in these things from first source, which is at 1000 Kelvin, and 100 kilojoules of heat is being transferred to the cycle, and next source which is at 500 Kelvin and which is transferring 50 kilojoules to the cyclic device, and at the end we are having a sink which is at 300 Kelvin which is getting 60 kilojoules from the cyclic device. Okay, in the option we are having option A, it says that it is a reversible heat engine. Option B says it is a reversible heat pump or reversible refrigerator. Option C says an irreversible heat engine. Option D says an irreversible heat pump or an irreversible refrigerator. Here, straight away we'll be having an idea. We can find whether this cycle is reversible or irreversible, right? By just using Clausius inequality by cyclic integral of dq by t. Don't worry, while going through the concept, you will understand how to approach these problems. I'm just giving you a familiarity. So straight away we can find whether it is uh, reversible or irreversible by seeing what is the value of coming after cyclic integral of dq by t or summation of dq by t. How to find whether it is a heat engine or heat pump or a refrigerator? Let's see that. Here the cyclic device